Okay, like that. I still got some food, stuck in my windpipe, so. All right. So what we'll do today is we're going to go through another test. This is actually kind of interesting. In one of my other classes, we kind of looked into various things related to security. It's an Android programming class, so we started off with this one. Basically, the CIA has collected a lot of zero-day exploits, not previously known. And one of your classmates here, also worked on the kernel code of Android and discovered a lot of memory leak issues. So apparently, people who work on the Android operating system on mobile devices tend to slap on rather sloppy code, let's just say. So it's kind of interesting. And then we went from there to norsecorp.com. And for those of you who have not seen this before, it's a live image of cyber attacks. And the direction of the projectiles indicates, where it's originating from, at least the launching computer, not necessarily the origin of the hacker. And somebody asked a very good question, how come there's nothing coming from Russia?
Because Russia mirrors all their stuff off of other computers in other countries.
I think there might be a filter applied somewhere because it doesn't seem to make sense that there are, because there's nothing at all coming from Russia.
The attacks are launched out of Russia.
Well, it is also possible that they're very smart and they don't use their own computers to launch the actual attack. Okay, they basically use a botnet, hack into somebody else's computer, and then use that computer to launch the attack. So it never shows, it never traces it back all the way to the point of origin. So, interesting stuff.
How's the website? How is it called?
Norse Corp. NORSECORP.com. And once you get there, it will give you a live attack. And that's the animation that we saw earlier. Yep, so you can see all the exchanges. And we don't have enough resolution to actually read the text here, but you can actually see the attacker IP, attacker geo, which is the location, target geo, attack type, and also port number. So it's interesting. It's just a visualization of all the attacks that are kind of going on. So this is the website, norsecorp.com. Kind of interesting stuff. And also, for the ultimate, if you're into this type of thing, one video that we also watched in the Android class had to do with Jeep hacking. How many people have seen that video or has read that article? Okay, it's pretty unsettling, isn't it?
Yeah.
So basically, somebody can hack into your car's control system. I think it's going through the phone's Bluetooth connection, right?
No, they actually have their own built-in cellular modem.
It's a cellular.
Yeah.
It's a cellular.
Oh, it has its own. Okay, so there's no way to turn it off then.
Yeah. It's a cellular connection.
So there's a cellular connection, and they were able to. So it started off with something annoying. So these two guys, they're known hackers, and they're just doing this as an experiment. So the other guy is like, okay, show me how you can hack my car. So he was driving on the highway. So it started off with something that's really kind of annoying, like they turn on the fan first, okay, crank up the fan speed all the way to maximum, So the guy like, I didn't do that. Okay, that was kind of annoying. And then they switched to a channel, blast the music. So it started to get really kind of annoying. And then they turned on the windshield wiper with all the windshield fluid, the washer fluid, squirting and all that. So the guy said, I cannot even see anything on the highway. And then they said, let's do it. And then the two hackers looked at each other remotely in the living room. They looked at each other and go like, should we do it? Yeah, do it. They click the key, and then they kill the engine. And then the guy was actually on the highway, and you kill the engine. And this is a Jeep. It's not very aerodynamic, right? So it slowed down pretty quickly. And the guy kept saying, no, turn it back on. I'm on the highway. This is actually dangerous. And then the two hackers just kind of laughed. And then they said, we cannot turn it back on. You have to turn off ignition and turn back on again. So that's what he did. Yeah. So it's, and this is such a regular Jeep, and it was filmed in 2015, I think. So it's 2 years ago. You can kind of imagine cars will be more hackable in the future. Yep. Go ahead.
There's actually a lot of different models of Chrysler that are also susceptible to the same.
Yep.
And they didn't show it in that particular video, but at DEF CON, they went over in depth how to get it, and they showed that they could actually
steer,
ping a cell phone network, and see every single car that is exploitable that's on the network at a given time.
Wow.
So you could actually theoretically target a specific car, but you could only target the car when the car is on, and when the car is on.
Okay.
You could actually target.
So when ignition is on.
Yeah, they could filter the. It wasn't the IP address. It's like an MSIP. It's almost like an IMEI of the vehicles. So you could if you do the IMEI of the car, you could target that IMEI once that car is on.
Yeah, at low speed, you can actually take over steering too. I think that was
You could turn off the
in the
brakes.
video. Sorry?
You could turn off the brakes. So you could keep the car running and turn the windshield, turn the squirters on, and turn off the brakes. And just
You could turn off the brakes.
You mean engage the brakes or disengage?
to where the brakes don't work.
Disengage the
You just
pedal.
disable the brakes.
Oh, that can be bad. It's interesting how this never made it really to the news, mainstream. All right, well, as promised, so we're going to start with exam 2, and this is 1 year ago, just about. Yeah?
Is this in the shared folder?
This is not in the shared folder yet. I can put it into the shared folder. So make a copy, and we'll designate it as 2016 Spring Exam 2. And I can choose a different folder. Oh, I can just copy it to a different folder. There we go. Okay. Now it is in the share folder. All right, so let's go ahead and start with this one. Question number 1. I think this should look familiar now because it's about the same question in the other practice exam. So the question is saying, via lab testing, it is known that a particular data transmission mechanism has the following data rate or error rate. When the one is transmitted, there's a chance of 2% chance that it will be received incorrectly as a 0, and a chance of 98% that it will be received correctly. And if a 0 is transmitted, there's a chance of 4% that it will receive incorrectly as a 1, and a chance of 96% that it will be received correctly as a 0. So the question is asking, suppose a 4-bit pattern, 1001, is transmitted. Assume the transmission of a bit does not affect the error probability of any other bits. We want to analyze the overall error rate in the following space. Create a table so that each row represents a data pattern that can be received. And then on each row, use a formula to express the probability of that particular pattern being received. And there's no need to work out the exact numbers, because some people may not have brought along a scientific calculator. So you can just use variables to reuse the same formula to save space. Okay, so that wink wink, which means this can significantly help you simplify what your table would look like. Note that the summation of the probability of each row should add up to exactly 1. So if you add up all the rows, you should add up to 1, because the probability should be 1 when you add up every single possibility. All right, so are there any questions about what is being asked? No questions? Okay, all right. So let's work on this one. I'm going to cheat a little bit here and actually use a spreadsheet to work on this. So let me go to the shared folder and use a spreadsheet. And I'll rename the spreadsheet to the correct test. So this is Spring 2016 Exam 2, Question 1. All right. So can someone give me the possible patterns that can be received? Let's go back to the question first, so that this way we know what we are dealing with. Okay, with all these, where is it?
There's 16 different patterns.
There are 16 different patterns. Very good. Okay, why?
Basically 0 to 16 in binary.
Okay, very good. So the first thing we can do, I'm just going to try to go back to the question first, so that this way we can look at the question and then we can look at the answer. I thought I put it here, 2016 spring, that's the final exam. Where's the actual test? Did I put it there?
It's under recursion.
I put it into the wrong folder?
No, it was under recursion before this test. That's where I pulled it out.
Oh,
If you go to recursion section, it's over there.
but I just copied it today too. Oh, right there. That's the answer.
Is it the one with fx instead of x?
Or did I put a?
Maybe it's on the title.
This one is no. This one. This is the actual final exam.
Oh, okay.
Okay. Let me just get rid of all the other stuff that I don't need. That's what it like. That's what it's like, to program in using Android. You have to look up so many things,
And then it still doesn't work.
and then it still doesn't work. Yeah. Assembler, opcode. Yep. They're all on the same page, but at different parts of the same page. This is where I got some of the icons for my app. There we go. Okay, this is the one. This is the question. Yep. Did I put it into the wrong class? Does anyone, can anyone access?
I don't know which file name is it.
I think it's 2016 Spring Exam 2.
That's not in there.
It's actually in there in PDF form in one of the sections on Google.
Yeah, there's 2016 Spring FX, and then it's on Moodle under recursion.
Okay, under recursion. So in Moodle under recursion, there's also a link over there. But I'm going to try it one more time to make a copy of this. Problem is my screen is not big enough to let me know which folder I'm actually in. Share folder. So it should be here. Share it with the same people. Yeah, we can do that.
Yes, right.
I'll do one more time. Spring 16. Maybe because I did not allow it to open previously, it actually did not go through the whole operation. Now it should be there. Can someone confirm that? We have exam 2. Yep, I can see it over here. Okay, so because of the pop-up block, it did not pop up, and if it did not pop up, the move or the copy action actually did not go through. Okay, so now I know. All right, so this is the question. So one way we can do this is to look at it as a picture, as a tree. Okay. So I'm going to use a node to represent what is transmitted, and then use an edge, a labeled edge, to designate what is actually received. So the first bit transmitted is a 1. So there's a node of 1 here. And then we just draw 2 edges, because it can be received as a 1 correctly or received as a 0 incorrectly. So it can be received as a 1 correctly and received as a 0 incorrectly. The probability of going to the left-hand side is 0.98, and then the probability of going to the right-hand side is 0.02. Is that okay? All right. So now we're dealing with the second bit. The second bit is a 0 being transmitted. It's also going to be a 0 on this side, because remember, a node is representing what is transmitted, and then the label of an edge is indicating what is received. Are we doing okay so far? So this is not your usual binary tree. It has nothing to do with your usual binary tree. So with this one, once again, with a 0, it can be received correctly as a 0, can be received incorrectly as a 1, and so on. Is that okay so far? And because we have 4 bits transmitted, so how many leaves are we going to be talking about at the bottom of this whole thing? Every level is introducing twice the number of outcomes, right? And then how many levels are we talking about? 4 levels, because there are 4 bits transmitted. So by the time we get to the leaves, how many possible edges are we talking about at the bottom level? 16, 2 to the power of 4. Okay, so that is absolutely correct. So we'll go back to the spreadsheet. Because now we have to go find the spreadsheet. Where is it? Oh, right there. Okay. So now we can say, okay, now with a spreadsheet, there are several ways to do it. You can just do it the usual way. I personally like to do it like this. 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, and so on. Okay, because you're going to do this on a piece of paper, you just have to make it systematic so that you don't accidentally miss one. When you're doing this using a spreadsheet, there are tricky ways that you can do this just using a spreadsheet to do all the base 2 conversion. Okay, so I'm just going to work out a few, because otherwise it would just be kind of boring. How many people want to look at the entire table? No, not really. Okay. All right, so we'll just pick out a few. Like pick out maybe this one. This is a good one. So we'll pick out this one and ask. Okay, we'll go back to the question and find out what we are asked to do. On each row should represent a data pattern that can be received. So on this side, this is representing that we are receiving 0011 despite 1001 being transmitted. Oops. And then over here, we also want to use a formula to express the probability of what data pattern, of the probability of that particular data pattern being received. So we want to go back to the spreadsheet and say, okay, but what is the probability of receiving 0011? Okay, is the first bit received correctly? No. And what is the probability of not receiving the first bit correctly? In other words, we're asking what are the chances that a 1 is transmitted, but a 0 is received instead. 2% chance, 0.02. Okay, so it's a 0.02 for the first one. What about the second bit? The second bit is a 0 transmitted, and it is received as a 0 correctly. And according to the question, what are the chances of that happening? 96%, which is 0.96. Okay, very good. The third bit was a 0 transmitted, but it's received as a 1. So the chances of that happening is 1 minus 0.96, which is 0.04. And then the last bit is received correctly. It is a 1 transmitted and is a 1 received. So that means the probability of that happening is 0.98. So when you multiply these four numbers, it becomes the probability of having 1001 transmitted but received as 0011. Is that okay? So you can probably figure out that there are a few rows with the same number. So you can just give this number a name or label and just refer to the other rows and go like, okay, this row has exactly the same number. Can someone give me just a quick answer, okay? Which row or which data pattern will have exactly the same probability? 1100, very good, because it's just the opposite pattern. Okay, very good job. Okay. There are four, I think there are at least four with this probability. Because there's 0011, 1100, there's also 0101. And then the flip side of that. Yep. So the actual distinct values are not that many. You just have to kind of find out the pattern, and then you can reuse the same row or the same values. Are there any questions about this one? Do you think this is related to question number 1 of your practice exam before the break? This is just the flip side of it, right? This one gives you the probability, and you have to tell me the chances of receiving a particular pattern, as opposed to the other one, which gives you the observations, the frequency of observations, and you have to figure out the probabilities. Is that okay? All right. So let's go ahead and move on to the second question. The second question is also, it should be very familiar, because we start off with a recursive definition of f. So this is given to you, okay? The definition is given to you, function error, okay? It's actually a function f, but for some reason, Firefox cannot render that equation correctly in Google Documents. And the only way to fix this problem is to use another browser. This is one of the very few instances where Firefox actually does not work in terms of rendering something in Google Documents. So I'm going to use Google Chrome for this because it just annoys me that it's not working correctly. So we have go. And you can see the fonts are slightly different too. And this is in Google Chrome. You can also see in Google Chrome, the spacing is different. The vertical spacing is a little bit different. But that part doesn't bother us because we're only looking at this on the projector. All right, so we're getting back to this. Function f is defined recursively as follows. F of 0 is defined to be 0. And then for all the other f's, f of x is defined to be f of x minus 1 plus 2x minus 1. Okay? So it's very similar to the one that you have to deal with in your own practice exam. So the hypothesis, okay, the theorem is, hey, f of x may be just as simple as x squared. Okay? But that's a theorem. We need to prove that. Is that okay? Because in a question like this, you have to identify which one is given to you and which one is suspected to be a theorem, and you have to prove it. This is the suspected theorem, okay? And so this is what you need to prove. The other part, which is here, this is given to you, okay? I'm telling you how f is defined. This part here is just saying, well, maybe f can also be defined like this and is identical in terms of the values compared to the recursive definition. Are there any questions before we move on and actually do the proof? No questions? It's very similar, yes.
It's like if it's assume that it's true for n.
Wait. Okay, you're jumping a little bit ahead. What you said is right, okay, but not yet. Because it's just the ordering thing, because typically we would like to there are two steps to prove by induction. Which step do we usually start with? The base case, okay? Base case, because you need a base case to connect to the anchor first.
Right.
Yep. Yep, exactly. So you have to find a natural end of the range of the values that this thing has to work on. In this case, it has a very natural end, which is 0. So you say, for the base case, so in your answer, it is really helpful if you just, clearly spell out this is the base case, okay? So I don't have to guess, oh, are you talking about the base case or is this the induction step? So in the base case, you say, let's x equal to 0, okay? So you say when x equal to 0, f of 0 equals to 0 by definition. Okay, that's cool, because you're just quoting what is given to you by definition. But then you can also say 0 squared, okay, I'm going to insert equation here. So 0 squared is also 0, or I can use this, x squared is 0 squared is also 0. So by using this, then we can say base case is proven. Is that okay? Because f of 0 is 0 by definition, but x squared is also 0 when x is 0. So I have established in the base case that you can call f of x squared. Is that okay? Okay, so now here comes the trickier step. The induction step is trickier. Because in the induction step, you have to first say what is assumed. Okay? In the induction step, there's an assumption and say that, okay, let's just say that the theorem is true for x equals to n already. Can we prove that it is also true for x equals to n plus 1? Okay, so you have to state the assumption. So assuming the theorem is true when x equals to n, need to prove the theorem is also true when x equals to n plus 1. Okay? Now, if you run out of time at this point, but you finish this particular sentence, you will still get partial credit because I want to know that you understand the structure of a proof by induction. Okay, the steps are important too, so you won't be getting full credit if you run out of time at this point. But you will get partial credit if you just spell out the steps or the structure of the proof itself. Okay. So the step of the actual proof is going to be, so you have to kind of help spell out what is the assumption. Okay. So assuming the theorem is true when x equals to n, so you might want to elaborate on this. Okay. Meaning, so meaning f of n is proven to be n squared. Okay, I'm gonna use equation here. F of n is n squared. Because that's what it means when we have the assumption of the theorem being true when x equals to n. Okay. So now you can go ahead and try to prove it. When you prove it, you have to combine the definition along with the assumption. Okay. So that those two things are both important in the proof. So I'm going to use the equation along each step. So the first one is to say, okay, we want to figure out what is f of n plus 1. Because we want to show that f of n plus 1 is n plus 1 the whole thing squared. So we start with f of n plus 1. So the first thing you need to do is to go by the actual definition, which is all the way up here. So f of n plus 1 is actually f of n plus 1 minus 1, okay? Because this part here is subtracting 1 from whatever is in the parentheses, okay? And then we say plus 2x, but we don't have x here, we have n plus 1, so you have to say it is 2 times n plus 1 in parentheses, and then do the subtraction of 1 as the last item. Are there any questions about this particular step? I'm just simply plugging in n plus 1 in place of x in the definition of f. Is that okay? So I can immediately, well, not quite immediately, but I can do one simplification, and then I can use the assumption in the induction step. So on the second line, I'm going to say, okay, there's no alignment tool to align this easily in the Google equation, so I'm going to have to do the approximation here. So this becomes f of n, right? And then I can also simplify the rest. So I get 2n here, and then we have 2 minus 1, which is a single one left. Are there any questions about the simplification from the first line to the second line? Is that okay? All right, okay. So from the second line to the third line, we will make use of the assumption of the induction step. In other words, now we say, oh, but we know what f of n is supposed to be because of the assumption in the induction step. So now we can look at f of n and go like, ah, but we know what it is. It is just n squared. The other part is 2n plus 1, right? So from your quadratic equation stuff, you know that this is just n plus 1 and then the whole thing squared. I have to use a equation again just to make the square look right. Okay, there we go. And that's the end of the proof. Are there any questions about number 2? Any questions about the steps involved or the structure of the proof itself?
You have to. Would you want a conclusion? Like, therefore we proved that.
A conclusion would be helpful, but if you run out of time, you don't have time to do it, this is sufficient. Yep. So you can conclude, you can make a conclusion here. Conclusion, because the base case and induction steps are both proven, the theorem is proven. Okay, by induction. Okay. Shall we move on to number 3? So number 3, once again, has to do with coin tosses. We are assuming a coin is fair in this case. So any equal length sequence of head and tail have exactly the same chance. The probability of the sequence head, 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 tail, for example, is the same probability of the sequence tail, head, and that turns out to be 0.5 to the power of 4. At a casino, a coin is claimed to be fair. An observer took count of the results of many sequences. Each one is a sequence of 4 tosses. The observation is that after all the counting, there's a total of 79 sequences, ending up with 1 head and 3 tails in any order. So that means the head can be the first one, can be the second, can be the third, can be the last one. And a total of 146 sequences, ending up with 2 heads and 2 tails in any order. And what I neglected to say here is the frequencies of all of the other observations were lost. Okay? In other words, these are not the only outcomes out of the coin tosses, but these are the only ones that we remember. We basically lost track of all of the other number of. For instance, what about all heads and no tails? We lost track of those. Is that okay? All right. So in the first question, or part A, how would you check whether the coin is loaded or not? In other words, it probably involves some kind of comparison. So you have to tell me, what are you comparing against what? Is that okay? So how would you work on this one? I'm not telling you the total number of observations, okay? Unlike the practice exam before the break, this one doesn't tell you that I have observed 630 or 680 observations total. This one only tells you that out of all the observations, 79 are 1 head, 3 tails, and 146 end up with 2 heads and 2 tails. So how would you approach this? This will still have something to do with binomial distribution. Yep.
Use like the 79 to find, like try to find how many like trials there were, like the total number,
Mm-hmm.
and then do the same thing for 149 and see if those numbers are the same.
You don't even need to go that far, but that will work as well. Okay, but once again, we're looking at ratios. Okay, so we're looking at the ratio of what is expected to be the ratio of let me see, 1 head and 3 tails versus the ratio of 2 head 2 tail. And then we want to look at the probability ratio versus the observed ratio and see whether they match up or not. Yep, go ahead. Okay, so that would be the what I'm looking for. Okay, but I can write it down here. So I will see if it can handle this equation. Okay.
I feel like you're gonna like steer us this way, and then it's like the test is gonna have some like just completely off the wall question.
Well, since all of these are actually on YouTube, so it's not okay. So we are basically still looking at binomial distribution because there are 2 possible outcomes per trial, right? Okay, and then we have 4 trials per experiment. So we're still dealing with binomial distribution. So now we have to say, okay, out of these things, how many of these would have 4 heads, for instance? Okay. Okay, what is the coefficient of 4 heads? What do you think? There'll be one of those, right? But I'm not going to write 1 here because I want to use a much more general way to generate the coefficient of each term inside this whole thing. And what is that going to look like? Exactly, 4 choose 4. So we'll see whether this works. Oh, it actually works. Cool. So we are looking at 4. You can either use 4 choose 4 or 4 choose 0. Okay, it's entirely up to you because counting the number of heads and counting the number of tails is exactly the same thing. Gives you symmetric results. Okay, so you can do it either way. The second one is going to be 4 heads. 3 heads and 1 single tail. How many of those are we talking about? Well, we use choose again. This time it is 4 choose 3. Okay. I'm hoping this is starting to look familiar because this is what we talked about before the break. Okay, so we are still using the same kind of stuff here, except when we apply it, it's going to be a little bit different compared to the practice test before the break. So at this point, I'm not gonna. I'll just be a little bit lazy and just copy and paste it 3 more times. So copy and paste, paste. So the last one would have no heads left. So I'm going to remove all of the heads, and then the tails, there will be 4 tails. It'll be 4 choose 0. And then the second last is going to have 1 head and 3 tails. So tails, there will be 3 of those. There won't be any heads. And this becomes 1. And this will be 2 head, 2 tails. 4 choose 2, just like that. All right. Are there any questions about this part? Is this part okay? I can magnify it so it's just easy to read like that. Is that okay? All right, okay. So what are we learning out of this? Well, it tells us the expected ratios of 1 head, 3 tails, which is 4 choose 3, versus 2 head, 2 tails, which is 4 choose 2. Right? Okay. So now we can say the expected ratio of observed 3 head, 1 tail. I think that's in the question. Yeah, 1 head, 3 tail. Okay, never mind. 1 head, 3 tail versus 2 head, 2 tail is basically 4 choose 3, or 4 choose 1, it's the same thing. Okay, 4 choose 1 versus 4 choose 2. So I'm going to use the equation here. So we're talking about 4 choose 1 to 4 choose 2. Is that okay? Even without a calculator, can you figure out what is 4 choose 1? Anything choose 1 is easy, because it's just whatever you choose from, right? Okay, so 4 choose 1 is 4. What about 4 choose 2? 6, exactly. So it is just your 4 versus 6. What is the observed ratio? The observed ratio is just given with the numbers here, which is 79 versus 146. Versus 146. So you can probably tell right now that 4 to 6, this is not quite the same. We're off by quite a little bit. Is that okay? And the question is really just asking how would you check. You basically just have to tell me, you would compare this ratio, 79 to 146, to this ratio here, which is 4 to 6. You just have to tell me that you're comparing these two. They should be close, okay? But exactly how close are we talking about? Since I did not tell you, what level of confidence I'm expecting, you don't have to say it. But you do have to point out that these two are the ratios that we are comparing. Is that okay? All right. Part B is asking if you figure out how to check whether the coin is loaded. Also indicate how you figure out how the coin is loaded. I mean, how heavily is it loaded? So all you have to do is to say, check. We want to evaluate the difference or the magnitude of the difference between the expected ratio and the observed ratio. And the last question asks, assuming the observation is representative of the nature of the coin, present equations that can be used to solve the actual probability of a head versus a tail outcome after a single toss. In other words, I want to know, assuming what you observe is representative of the behavior of the coin, I want to know the probability of a head in this case. How can you figure that out?
Basically, figure the probability versus see how far off the heads are from the tails, and then you would know what the probability of head is, so you know that's not 0.5 if it's off.
Right. We kind of know that it's not 0.5, okay, because of the first two parts. So this part is saying, assuming what you're observing, the 79 versus 146, is actually representative of the behavior of that particular coin. What is the actual probability of landing on the head after a single trial? That's what it's asking. Okay. So how would you tackle that problem? So we go back to this equation here, okay? What do you think is represented by uppercase H and what is represented by uppercase T? The probabilities, okay? So uppercase H is actually the chances of landing on the head after a single trial, and then T, uppercase T, is the actual probability of landing on the tail after a single trial. They add up to what? H plus T is always 1, okay? So it seems like, hey, this is useless. This is entirely pointless because 1 to the power of 4 is always 1. Well, we know that part, okay? So we're not questioning what is the actual value of this whole thing. What we are interested in is what is this whole thing and what is this entire thing? Are we still okay so far? Is that okay? So we know that 4 times this thing and 6 times this particular thing, we know the actual observation now because that's given to us. Okay. Okay, so let me just write it down here. Okay. Where is it? Right here. I removed the extra page break, so I'm going to put it back here. All right. So what we want to do here is assume. Okay, I don't want boldface. Assume T is the total number of observations, which we don't know and we don't really need to know it, but it helps to have this symbol here. Okay. So what we know is T times, okay, so let's use the equation here. So we know T times 4 choose 2 times, in this case, h times t to the power of 3. We know this is, oh, I shouldn't use t here, because t is already used for tail. Let's pick another symbol. We'll just pick n. Sorry about this. So I'm going to fix this to be n here. Okay, so we know this number to be what? Well, first of all, what is this number representing? H is the probability of a head, tail is the probability of a tail. So 4 choose 2 times ht cubed is the probability of observing an experiment that ends up with 1 head and 3 tails. Is that okay? N is representing the total number of observations or total number of experiments that we have observed. So what is n times that ratio? How does it relate to something that is given to you? Which number are we talking about?
The number of times you expect 1 head and 3 tails for that many trials?
It is exactly, well, it is talking about this number here, 79. Okay, so we can plug this 79 into this equation here. So this by itself is not enough to solve the equation because we don't know what n is. N is unknown. Right? But we have another equation similar to this one that can be very helpful. So the second equation that we can also write is starting with n again. And I made a mistake here, excuse me. This is supposed to be 1. And then this one is 4 choose 2 h2 or h squared t squared. Okay. And according to the observations, how many experiments ended up with 2 heads and 2 tails? 146. Okay, very good. So now we have 146 here. All right, so given these two equations, can we solve for the values of one of the h or the t? Because if you solve for one, the other one is easy. And how would you do it?
Substitute 1 minus h for t.
You can do substitution, okay? You can also do a division. You can use a division to get rid of n.
Yeah.
And also h is just 1 minus t, so
Yeah.
there's a whole bunch of ways to do this. Is that okay so far? So if you get this far, you will get a lot of partial credit, not all the partial credit, because you have to show me the final equation to solve for either t or h. So let's go ahead and do this part. So I would personally do a division. So I'm going to do a division, which is 79 divided by 146 on one side. And then the other side is going to be the two equations. So once again, it is a fraction. So we have n, and then we have 4 choose 1 ht cubed. And then the bottom one is going to be n times 4 choose 2 h squared t squared. Okay? How would you simplify this equation? I mean, it's, well, n is canceled out, right? We like that. So we have, the top one has a 6, I think. Oh, I think I got the numbers. Did I get the numbers right? 79 of one head, three tails. And okay, it's correct. Okay. So n cancels out. So we never really need to know what n really is, okay? Because n cancels out. So on the top we have a 4, and then one of the h's canceled out. We have just t left here on the top, and then on the bottom we have 6h, right? I think that's right. Is that right? Okay. But then we can also rewrite that. Okay.
2/3.
Sorry. 2/3, and then we also know how t and h relate. So you can now say, do another step. You have 2. Either one is fine because we can express t as h or vice versa. So I'm gonna do it like this. It depends on what the question is asking. The question is asking, present equations that can be used to solve the actual values of a head versus a tail. So either one can be solved. Okay, 3h like that. So if you get to this point, I will give you full credit already, because at this point it really is just algebra to solve for h. But that's what the question is asking, is to get down to this level where you have one single equation with one single unknown, and to solve one unknown from one equation, we can just assume that's algebra and not going to be a problem. But are there any questions about this? The answer of part C. Yep.
I have a question about part B actually.
Part B? Okay.
Was that your answer for it? What you put there, or was
Yep.
that just a?
That's just my answer. That's what I'm expecting you guys to say.
Okay.
Or something to the effect of that. You're just comparing the two ratios. If they're further apart, then the higher probability that the coin is not fair. The closer they are, the more probability that the coin is actually fair. Which is kind of intuitive or kind of common sense. Yeah, go ahead, Shane.
No, I was like, I got everything down except for like when I was doing it, I didn't get how you got the 1 minus h. I get it now, like what you put in there.
You got it now?
But when I was doing it, I basically had 79 over
146
equals 0.25 over 0.375. It's the same ratio.
Okay.
But I couldn't. I was like, how do I get a variable in there? So I was like stuck on the like.
Because h and t are variables, but they are not independent because h is 1 minus t and t is also 1 minus h. Those are complements of each other. Because they have to add up to 1. The probability of landing on the head and the probability of landing on the tail, they have to add up to 1. Is that okay? Any other questions about this one? Yep.
Would you have to put it in a single variable to get full credit?
Yes. Which is actually not too hard because all I did here was to re-express the t as 1 minus h.
Yeah.
But that part is actually important because it tests whether you understand how h and t relate, because they are complements of each other. Okay. Any other questions about number 3? Is that good? Okay. Shane, are we good? Okay.
So I get like the 0.25 is my t basically, but I just put them all in terms of the same variable.
Okay. What about the rest of the class? Are we ready to move on? Okay, all right. So number 4 is probably the harder of the 4 questions because this one is not presented in your version or the practice test before the break. So I give you an algorithm. I give you the search algorithm. This is a linear search algorithm, okay, which is one of the first algorithms that you're introduced to, or one of the first. You're given an array A, you're given n, which is the number of elements in the array, and we assume that n is actually correct. K is the value that you're searching for, okay, or the key. And the following function is supposed to return non-zero if and only if k matches the value of at least one element in the array A. Is that okay? So when you look at the algorithm, the linear search algorithm, it's nothing really exciting, okay? I have a local variable I, which serves as a variable of an index. It is initialized to 0, so I do the search from the beginning of the array. As long as I haven't seen everything in the array, and I haven't found a single element with a value of k, I increment the index variable, so I'll be ready to compare to the next element in the array. After I get out of the loop, I return I is less than n as if it is the correct answer. So now the question is, I know this is correct already. I know this algorithm is correct. How do you prove it? So I want you to prove by contradiction that this algorithm is correct. Okay. Now you don't have to do this symbolically. Okay. Several people ask me, oh, so do we have to do it symbolically? No, you do not have to do this symbolically, but you do have to use the structure of a proof by contradiction. So that part is required. And then the second one is you have to use logic to explain to me why you think this algorithm is correct or how you arrive at contradictions. Okay? Are we doing okay so far with this code? Does everybody understand the function itself? Is there anything in the function that you want me to explain? Okay. No particular questions? Yep.
So because the plus plus is before the I, is that gonna?
Doesn't really matter because no one is really using the value of this entire expression. So the side effect of actually increasing I by 1 is the only thing left.
Okay.
So this is really the same thing as I equals I plus 1. Okay. I would point out one thing that is actually very important, but some people may not understand the importance of that. When you do conjunction in C and C++ and most other programming languages these days, it is short-circuited, which means it always evaluates from left to right. Okay, that part is important. And then the second part is if the first part of a conjunction is false, it doesn't even bother to evaluate the second part. Okay, so the short-circuited nature of Boolean expression evaluation in C and C++ may be important. Okay, that's one of the things that you might want to remember. Yep.
So the n that's passed in, is that the size of the array?
The number of elements in the array or the size of the array, correct.
Okay. So
Because
then
go ahead.
that wouldn't be a problem if it short circuits then, right?
It would not be a problem if it is short-circuited. It would be a problem if it is not short-circuited.
Yeah. Okay.
Because if it's not short-circuited, when I equals to n, you will still try to evaluate the second part. Now in this case, it would not really impact the correctness of the outcome because by the time I equals to n, the first expression would be false, making the entire conjunction false to begin with.
Yeah.
And then the second one is only comparing a bracket n with k, which is not changing it, right?
Yeah.
So whether it equals or not really doesn't change the correctness of the algorithm. But you are correct that in many other situations, it is important that it is short-circuited because if the second one actually has a side effect of changing a bracket I, then you'll be changing a location where you're not supposed to. And Qualcomm probably have code like that too.
So aren't you checking, isn't A a two-dimensional array?
It's single. It's a, ooh, okay, yes it is, my mistake. Okay. There are two ways to fix that problem. I can make this a pointer too. But you're right. Okay, A is supposed to be a single-dimensional array, so you either use the asterisk or you use the square bracket. Good observation. Good job. So good thing I don't work for Qualcomm, huh? Because I'll be adding more sloppy code.
Wouldn't surprise me at this point.
No, I was never employed by Qualcomm, so I. Okay, so, all right. How would you approach this problem? What is proof by contradiction, and how do you get started with this one? What is the theorem? Yep.
Can you start by assuming the negation of the theorem?
Okay, so that's good, but what is the theorem? The first thing you need to do is to tell me what is the theorem? What are we trying to prove here? Okay, so here proof by contradiction that this algorithm returns non-zero if and only if there's at least one element in the array A with a value of k. This is the theorem. Is that okay? So the theorem is, the algorithm is in fact correct. It returns non-zero, but the key part here is we're working with if and only if, okay? If and only if there's at least one element in the array A with a value of k. Okay, so now we have to remember what exactly is if and only if. How many people remember what is if and only if? Okay, very good. So how do you negate an if and only if? Because proof by contradiction requires that you negate the theorem, and the theorem itself is, if and only if, using if and only if as an operator. So how do you negate a if and only if? Well, same thing that you do any other negation. You have to express if and only if in conjunction and disjunction and negation first, then you can go ahead and negate it. Okay, you can apply the negation. So we'll go ahead and do this step by step. Let me set up the document canvas. It might take a little bit of time, but I think in the end it helps because it can help save you time. You don't have to type or handwrite everything. Then you can focus on the idea, the concept. There we go. And I need a pile of paper. We have it here. Although the paper got smaller, so I don't need the stand anymore. See. Okay, in fact, we can make it lower too. There we go. And just leave a pen. Okay, there we go. All right. So instead of using that whole thing, this is the part where I don't like because all you can see is my big fat fingers, and until I move away, you can't really see what I'm writing. So we're dealing with something where the theorem itself is A if and only if B, which is equivalent to. Is that part okay? Does everybody understand that if and only if is the same thing as is equivalent to? Is that part okay? Yeah. All right, cool. So we want to apply negation to this thing because we are proving by contradiction, which means you have to do a negation of the theorem that you're trying to prove in the first place. Okay, so we'll go ahead and say, well, we'll leave the negation, we'll handle it later on because we have to re-express A is equivalent to B in a way that negation can actually work. Okay, so how do we express A is equivalent to B in operators that we understand more elemental? Go ahead. Okay, very good. So that's the first one. A implies B, and B implies A. Okay, very good. We're getting closer. In fact, we can apply negation now because the negation applies to the conjunction, and we know De Morgan's law. Hey, we can do this. Okay, cool. So we can now distribute the negation to the inside of the conjunction. So now we have a negation of A implies B. We have a negation of B implies A. And we have to change the conjunction with a disjunction because we have to replace the conjunction with a disjunction because this is part of De Morgan's law. So now we have a negation applied to a implication. How do we deal with that? How do you re-express implication so that we can reduce it down to things that we can actually negate? Not A or B. Okay, very good. So not A or B is this one, and then the other one is not B or A. Okay, not B or A. Is that okay so far? Okay. So now we have the negation of not A or B, which means we have to apply De Morgan's law. So we're distributing the negation into the inside of a disjunction and then change the disjunction into a conjunction. So that means we end up with the negation of A and B, and the negation of B on one side, and then on the other side we have the negation of B and the negation of A, like so. Is that okay? All right. The negation of the negation is double negation. We can simplify that. So we have A and not B, or B and not A. Are we still doing okay so far with this? Okay, so now we say, okay, what exactly is A and B? Well, those are pretty big terms, right? So A is basically saying, the algorithm returns non-zero. That's A. What do you think is B? If you look at the original theorem, what is B?
K is in the.
There is one element in array A with a value of k. Okay, so I'm gonna use a notation here that you should be somewhat familiar with. Okay, so I'm just gonna say there exists a j such that A bracket j equals to k. Would that work? Okay, because this saves me a lot of writing time. Now we start to understand why mathematicians like to use these symbols, because it's just a whole lot more concise. Are we okay so far at this point? Okay? All right, so given that this is what we are trying to say, this is not possible because it's the negation of the theorem. This should lead to contradiction. But because this thing is an OR, you have to show that each side of the OR is by itself a contradiction. Okay, it's not sufficient to only show one side of the OR is a contradiction. You have to show both of these things are contradictions. Okay, well, we can do it one at a time. So we will first start with A and not B being a contradiction. So once again, A is returning non-zero, and then B is there exists J such that A bracket J is K. Okay, so I can now remove the other one and focus on just this part. Okay. Well, by itself, there's nothing can do to prove this is not possible or this leads to false. Because what we need to do is to relate this to the algorithm. Okay? So we need to take a quick look at the algorithm and just kind of focus on what we're trying to do. We're trying to say that if the algorithm returns a non-zero, it is not possible that there is an element, oops, I take it back. It's the negation of B, so that means, okay, B itself is this thing, so when you apply a negation, you're basically saying, there does not exist a J such that A bracket J equals to K. Okay, so I have to correct myself just a little bit there. Is that okay? Which means, if this negation applies to this whole thing, that means this entire side is saying for all J, A bracket J does not equal to K. Is that okay? None of the elements in the array has a value of K. Is that okay? And we are trying to show that these two cannot happen at the same time. If the algorithm is returning a non-zero, it is not possible that none of the elements in the array has a value of K. Is that okay? So now we have to go back to the algorithm and say, why is that not possible? Why is that impossible? I'm returning a non-zero, which means I is less than n is true. If I is less than n is true, why is it impossible that every element in the array A does not equal to K? Why is it not possible? Okay, so you have to look at the control structure. Yeah, go ahead. So you have to look at the control structure, and this is why a goto is not a good thing. This is why break is not good. This is why continue is not good. This is why having a return in the middle of a loop is really, really bad. Yes?
Would
not necessarily. If I is less than n, there is still a chance that you can exit the loop. Because the loop, the condition of a loop is it a disjunction or a conjunction? It's a conjunction, which means do you have a higher chance of the conjunction, the whole thing being false, or a less chance that the entire thing being false? You have a higher chance because if at least one side of the conjunction is false, the conjunction is false, right? Okay. So it is entirely possible that I is less than n and yet you get out of the loop.
Because
It's entirely possible.
Because IA could equal K.
Yes, but that would contradict
That would
the
contradict-
assumption, right? It would contradict B itself,
No, no.
not B. Yeah.
And then you can prove that it's true.
So now there's contradiction. Do you guys see how that works? Okay, so let me repeat what I just said, but in a slightly different way. So let's just say that by the time we get to the return statement, I is less than n is still true. Okay, I is in fact less than n. Okay? But since we're out of the loop, and this loop does not use goto, has no return, has no break, has no other way of getting out. That means the condition j is less than n and a bracket I is less than n and a bracket I does not equal to k. This thing has to be false in order for me to get out of the loop. That's the behavior of a C program, right? But since we know that I is less than n is still true, that means the only reason why we are getting out of the loop is a bracket I does not equal to k is false. That got me out of the loop. But if a bracket I does not equal to k is false, it means simply that a bracket I equals to k. Do we have a problem with that?
No.
We do have a big problem with that because it contradicts with the statement. Okay, let me switch back to the document camera. It contradicts with the statement that every element in A does not equal to k because we just found one. That's a contradiction. So if you just explain verbally, this is a contradiction, we have done one half of it. Is that okay? So now let's work on the second half. Okay, so to work on the second half, let me just throw this back on the documents camera so that we know which part we are dealing with. We are done with this one. Okay, this one is already done. So now we have to work with the second part. Okay, so I'm going to use a second surface to do this. So now we have to say B and not A leads to contradiction. So let me just repeat what is A and what is B. B is there exists J such that A bracket J that equals to K. And then A by itself is saying returning non-zero, which means not A as a whole is indicating that we are returning 0. Okay, I'm gonna put this all the way in. Okay, get rid of the second slide, put this one here. This is the starting point of the second part of this proof by contradiction. We know at least one element in the array has a value of k that is given to you. Okay, but yet the algorithm is returning a 0, and we want to look at the algorithm itself and say, but that's not possible. It leads to a contradiction. It cannot happen. Is that okay? Okay, so looking at this, is not entirely useful because we have to relate this to the algorithm itself, to the code. Okay. So just remember this part. Okay, at least one element in the array has a value of k, and yet the algorithm is returning a 0. So now I'm switching back to the algorithm itself. So what this means is we are in fact returning a 0 here. Okay, it's returning a 0. But if it's returning a 0, it means I is less than n is false, which also means I is greater than or equal to n. Is that okay? Well, I itself is not a problem. Okay, if I is greater than or equal to n, obviously we'll get out of the loop. But that also means one thing, right? Because what it means is, what about the other values of I prior to this? None of those make the second condition in the conjunction true or false. So that means all of those elements of A do not match K. But we just said that at least one of them is going to match K. And there's the contradiction. Is that okay? I mean, does everybody catch the reasoning? I'll explain that one more time since we have 5 more minutes. Yeah, go ahead.
Are you using the short circuit to explain this?
You don't even need to use the short-circuited evaluation to get to this one. Okay, so let's go through the reasoning again, okay? So the reasoning goes like this. First of all, we are assuming that we are returning 0, which means I is less than n is false, which means I is greater than or equal to n by the time we exit the loop. Is that okay? So keeping that in mind, so that means what about all the iterations of the loop when I is less than n? Because I was initialized to 0. In order for I to get to at least n, it has to be incremented, because that's the only thing that I do to fi, is inside the loop I increment it, right? So I has to go from 0 to 1, 1 to 2, 2 to 3, and eventually I gets to n, and that's why we got out of the loop, right? But we didn't get out of the loop before that, right? So not getting out of the loop before I gets to n is telling you what? Exactly. It means this condition, a bracket I does not equal to k, remained true when I was 0, when I was 1, when I was 2, when I was 3, when I was n minus 1, right? But that's pretty much all of the indexes for all the elements. So that means we did not find a match prior to I getting to n, which also means that none of the elements of the array has a value of k. Is that okay? But that's a problem because this is saying that at least one element in the array has a value of k. We just contradicted it. Is that okay? So the second part is a little bit tricky because you have to argue and say that I is initialized to 0, and then every time you change it, you're only incrementing it by 1. So the values of I will go from 0, and then 1, and then 2, and then 3, and then eventually n. So you have to argue and say that, well, if at least one element of the array has a value of k, we would have exited earlier when I was a smaller value. We would not have to wait until I becomes n, then get out of the loop. So that's a little bit more tricky. In fact, you can probably find a proof by induction embedded in the proof by contradiction, but I'm not going to ask you guys to do that kind of proof. But do you see the argument? I mean, do you see the reasoning of this proof by contradiction? Okay. Is this also proving the algorithm will exit? No. It is only saying that if it does exit, it will be correct. So these are two different questions. Okay, so the one question is, when the algorithm exits, will it exit with the correct answer? The answer is yes in this case. But the second question is, will the algorithm actually exit, or can it possibly be stuck in an infinite loop? Well, in this case, it does not. Okay, but the proof here did not actually prove that this algorithm is guaranteed to exit. That's a question that will be asked many times when you move on to a algorithm analysis class at a 4-year university. So if you like this kind of problem, you're going to look forward to those classes at a 4-year university. Yep.
Once we contradict both sides, we're done.
Say that one more time.
Once we contradict both sides, we're done.
Yes. Because then you have shown it is false or false. So the entire disjunction is false.
Okay.
Alrighty, I'll see you guys on Thursday, and don't forget to bring your cheat sheet and whatever you might find helpful.